Welcome to Modern Physics. My name is Dr. Terrence O'Neill, and I'm going to be teaching this class in modern physics. Now, just a little bit about myself. I got my PhD at UCR, University of California, Riverside, in experimental high-energy astrophysics. I've been teaching modern physics for 20 years. I've been teaching at this institution, Riverside Community College, for nearly 40 years. I've also been doing research at the University of California, Riverside for 30 years in high-energy astrophysics. Now, this course right here, Modern Physics, is really at the sophomore, say even the pre-junior level of physics right here. Now, the math background in this class, as long as you know differential and integral calculus, you'll do fine in this class right here. It's 99% algebra and trig anyway, right here. Now, there is no textbook for this class. The textbook I use is this one that I wrote right here. It's just my big book right here, because I want to teach this class a little differently. I like to teach this the way I wish it was taught to me. So this class will be a lot different than most other, I'm assuming, modern physics classes, hopefully. Now, this class is broken down into 4 sections. One is relativity, the other one is prequantum mechanics, and then we'll do a little bit of a math review, and then quantum mechanics right here. Now, this is called modern physics. Well, when does modern physics start right here? Well, near the end of the 1800s, they had already known about Newton's laws by then, which are classical mechanics. They already knew about electromagnetism, and when you put it together, you got light. And so they knew about light and optics and sound and thermodynamics. And so they thought at the end of the 1800s that all of the laws of physics had already been discovered right here, and all we'd have to do is maybe find the constants to a few more decimal places. And there was just a few little strings hanging down that they had to just tie up. And when they tied up those strings, when they pulled on those strings, the whole ceiling fell and everything changed. Our whole notion of time changed. Our whole notion of space changed. Our whole notion of locality, that things only affect me by things around me, changed. Our whole idea of reality changed. So everything, all of physics changed right here. And it's that point where everything past that point is called modern physics. Now, in this class, we'll go from about 1900, we'll only go up to about 1930, because past 1930, the math gets quite a bit more difficult right here. So you might say, well, why didn't they find out about this? Why did it take till the 1900s to find out about all this changes right here? Well, if we were to make a plot here, and on this axis, I put distance or size, and on this axis, I put speed. And just to give you some scale here, first of all, there is a maximum speed, which we'll call the speed of light, and we're going to use c for the speed of light. So there is a maximum here. Also, for size, there is a maximum size. It's the size of the observable universe. Well, we believe the edge of the universe is out at about 46 billion light years. That's 10 to the 9th light years. Okay, remember, we can't see out there. We can only see things that hit our eye, but if we can project back, and we think that the universe is about 46 times 10 to the 9th 46 billion light years away. Okay, so everything in the universe, everything should be in this square someplace right here. Now, just to give you some scale, besides this, maybe I'll put in, say, 10 million light years. That's 10 to the 7th light years. Well, this is 46 billion. This is 10 million. If this were a linear scale, it would be way over here. But so I'm not making this a linear scale. And then we'll put in one other thing here. How about a dust particle? Okay, just to give us some scale. And then over here, we'll put in one besides the speed of light. How about 1,000,000 miles an hour? Well, this is really about 700 million miles an hour. So 1 million would be 1/700th of this, which would be just, less than the thickness of my pen right here. But I'm going to make it up a little bit bigger so we can see it. So this is going to be 1,000,000 miles per hour. Okay, well, before the 1800s, the only place we could test out Newton's laws, if we want to just put up here where Newton's laws have been tested and at least seem to be fall experimentally, well, if we just draw this little box right here, this little box right here is where Newton's laws, or sometimes they call this classical mechanics, is valid. So this is classical mechanics. Seems to work pretty good right here. And it's only been tested in here. They haven't tested it down smaller or larger than that. This 10 to the 7 light years is about the size of our local group of galaxies. So it's out there quite a ways. And it's never been tested above 1,000,000 miles an hour. So Newton's laws works pretty good, but there's no reason why it should work in these other regions. And in 1905, Einstein, just by pure thought, figured out that, this thing is just an approximation right here. And really, it's very close, but he said that if you look at this entire region, all the way down, all the way back up here, he found a mechanics. Remember, what do we mean by mechanics? We mean the laws that give the time evolution of a system, where things are going to be later. And this, he called this relativistic mechanics. Relativistic mechanics. Or a better name for it is special relativity. Special relativity. Okay, well, special relativity works going this way. Matter of fact, if you go down to slow speeds, it becomes Newton's laws. But you can't take Newton's laws in class and go this way. So it does work that way, but not this way. Okay, well, what about out here in this region, out here? Well, Einstein did this in 1905. And in 1916, Einstein changed relativity so it wasn't a special case, it was more general, and it included gravity. And that's over here. General is where, if you were working way out large, super large scales, you're going to be mostly using general relativity to find the time evolution of a system right here. Okay, so it was just the special, this is a general case of where you're accelerating. Special means the special case where you're not accelerating, you're moving at constant speed. Okay, he did this in 1916. Okay, and then down in this region right here, so you're smaller than dust and less than 1 million miles an hour, this is quantum mechanics. Okay, this was started by Einstein in 1905, but he started to not like this quantum mechanics. It didn't make sense to him, but other people picked up the ball, and you had people like Bohr, Heisenberg, Schrödinger, Dirac, that finished a lot of this quantum mechanics right here. And this took a while. Again, Einstein started it in 1905, but it wasn't well established until almost 1930. Let's just say 1930. Okay, so there's quantum mechanics. Again, Einstein didn't like it because this is very strange, right? And then we have this last region up here is what we get when we put together relativistic mechanics with quantum mechanics. So this is relativistic quantum mechanics. So this one right here so this would actually go all the way down right here. So this is relativistic quantum mechanics. Or quantum field theory, or, so there's a lot of names for that right here. And again, these things, all these rules tell you about the time evolution of the system. Again, these, when you go to slow speeds, include this. This, when you go down to slow speeds, but this is just a special case of constant velocity. This is accelerating systems right here. And so this works this way. You can't go that way right here, but you can go this way. Now, so what that means is, what do we have today? We have this rule right here, which again is relativistic quantum mechanics, or we could even call it the standard model. And we have general relativity right here. And this thing, if you go down general relativity down this way, it becomes Newton's law of gravity. So we've really just got two big theories in physics, and they don't mesh up right here. So that's the big problem right now. And that's why they like to look at black holes, because black holes is small, but gravity is strong. So they kind of, is where the two kind of meet right there. So in this class, we're going to spend the first, 25 lectures on relativity. So the first 25 lectures will be on relativity. Then we're not going to touch general relativity, and we're also not going to touch relativistic quantum mechanics. We're just going to hit this region and this one down here. But before we can go into this, we need to spend, this thing took 20 years or so to believe it, and so we have to go through some of the experiments that went on that slowly changed their minds, because this is radically different. So we call that a prequantum era. And so we'll spend about 10 lectures, 10 videos on this prequantum idea. And then before we go into quantum mechanics, we'll do a little bit of math review, mostly on just vectors, complex numbers, and maybe Fourier series right here, because we use it a lot in quantum mechanics right here. Most of our when we learned, and then the last 32 lectures or 32 videos will be on quantum mechanics. And when I hit quantum mechanics, I'm going to hit it a lot different than, say, the book, most modern physics books hit it. I'm going to go to the simplest possible system, which is the qubit, and just learn all of the rules of quantum mechanics. So we'll learn all the rules of quantum mechanics and then how we can apply it, whether it's through quantum computers or quantum cryptography or quantum teleportation. And then once we've beaten the qubit to death, then we'll finally go into one-dimensional systems, right? Just because they're simpler right here. The next simplest, and we'll try to look at we'll beat that one-dimensional system and see how the one-dimensional systems work. And then we'll go to the three-dimensional systems. That's where all the richness of quantum mechanics comes out. Especially we'll go to the periodic table, namely hydrogen, where we will figure out everything there is about hydrogen, all the way down to the internal structure of hydrogen, the fine structure, and we'll just beat it all to death. I figure if you really understand hydrogen, the rest of them are just more of the same. So we'll end up with, again, 32 lectures on this. So that's what this class is just on relativistic mechanics and quantum mechanics. And if you're taking any modern physics course or even taking quantum mechanics in your junior level, this class will definitely help you. Okay.